Okay, hello everybody, and thank you for joining in today's webinar. We're going to be talking about how we account for AC winding losses in the electric machine design process using Motor-CAD. So presenting the webinar today is myself, James Goss. I'm the CEO of Motor Design Ltd, and I'm supported by Mircea Popescu, who's our CTO, and he's going to be following up at the end of this the presentation with answering your questions, and he'll also be replying to questions in the chat interface as we go through the webinar. So a little agenda or an outline for today's webinar. We're going to start with a brief introduction to the company and the Motor-CAD software. We're then going to start with some theory on AC winding losses and then look at how we calculate those in Motor-CAD. We're going to compare the different methods or ways of calculating AC losses, and we're going to compare those methods on 3 different types of permanent magnet machine. We're then going to talk about how we account for AC winding losses in the thermal model and how we model our AC losses in the lab module for things like efficiency maps and duty cycles. We'll finish with a brief demonstration of the interface in Motor-CAD and some examples of doing some calculations of AC losses. Okay, so Motor Design Ltd produced the Motor-CAD software. Motor-CAD software is a dedicated tool for the design and analysis of electric machines. We like to work very closely with the customers, and we embed a lot of engineering know-how and experience into the tool. As well as developing the software and working with the software, we do our own design consultancy work, whether that's analysis or design work and training. And we're also involved in a number of research projects to progress the cutting edge of electric machine design. We tend to collaborate a lot with universities to develop our methods and models and create validation data for our simulations. So I'm going to talk a little bit about the Motor-CAD software, and then I'm going to go through the different modules, and then we're going to start talking more specifically on the AC winding losses. So the Motor-CAD software, as I said, is dedicated to the design and analysis of rotating electric machines. It allows us to rapidly and accurately model electromagnetic and thermal performance across the full operating range of a machine. It's designed and developed with expert electric machine designers, and a lot of the development has been driven through user feedback and response to requirements. It covers a range of different types of radial flux rotating machines, such as brushless permanent magnet machines, induction machines, and reluctance-based machines. And it uses a combination of analytical and numerical modeling techniques. So I'll talk first about the EMag module. It's based on a sort of a range of parameterized templates and geometries for the machines. So I've got here on the screen a few different examples of different machine templates: an interior permanent magnet machine, a switch reluctance machine, a synchronous wound field machine, and an induction machine. And the purpose of the EMag module is to calculate things like torque, power, losses, voltages, and currents. It's designed to be used in a very iterative manner, allow you to explore the design space in a comprehensive way, assuring that you've made optimal design decisions. The way that the electromagnetic module works is a combination of 2D finite element and analytical modeling. And we're going to show a little bit of that today and that philosophy with our AC winding losses. It's also coupled with the thermal model, so we pass losses to the thermal module and we can get back temperatures and iterate the solutions together. And again, we're going to show that today with the AC winding losses. It also automatically sets up different calculations for different types of performance tests or calculations that you might want to do. Within the EMag module, we have an embedded 2D transient finite element solver. When you do calculations which require the finite element solver, it automatically handles the meshing, boundary conditions, symmetry, etc. It allows us to do advanced calculations such as solving eddy currents in conductive components, and it also allows us to be a little bit more flexible with the geometries and move beyond the template, so we can do things like build, import DXF and script geometries. We can also account for effects, things like multi-slice rotor skew. It's quite powerful, and what it means is that engineers can account for complex electromagnetic effects early in the design process, and I think AC losses is one of those aspects, and it's something that we can demonstrate today. So I'm going to move on to the thermal module now. So Motor-CAD Thermal is something that we're very well known for, and it's really a standard tool for thermal analysis of electric machines with a really significant amount of experience and development over the past 20 years. The idea with the thermal module is it allows us to calculate steady state temperatures in the motor and also transient operating conditions. And again, it's designed to be iterative and allow you to solve things very quickly, so it allows you to explore the full design space. The thermal network in Motor-CAD is a lump parameter thermal network, and it is a three-dimensional network that includes both radial and axial heat transfer. It allows us detailed visualization and calculation of the cross-section of the slots. And although it's a lump parameter thermal model, a lot of CFD, FEA, and sort of empirical correlations are built behind the calculations of thermal resistances to get an accurate thermal model. On the right-hand side here, we're showing a couple of different slot cross sections, one for a concentrated winding and one for a hairpin winding. We're going to look at these two examples today. And then the final module that we'll just do a brief introduction to is the lab module. So when we're designing machines, particularly for some of the automotive and aerospace applications, it's really important to analyze machine performance across the full speed and torque range of the machine. And that's what the lab module allows us to do. It couples to both the electromagnetic and the thermal solver. And it allows us to calculate things like efficiency maps, torque speed curves, duty cycles, and do sort of replicate tests that we would do on the dynamometer. It automatically applies control strategies to replicate performance as we would have with an inverter. And it's very useful for designing for these types of applications. The way that the lab module works is it works by sort of building response surfaces of the machine initially based on the FEA and EMag solvers. And then it combines that with the thermal solvers and the control strategies to give you some of the outputs that I mentioned earlier. Again, it's as with all the other modules, it's designed to allow you to do all these calculations within minutes and allows us to iterate and explore the design space and try lots of different topologies and different design choices. One of the nice things that we can do in lab, and this kind of brings together all the different solutions, is to output the machine performance as a peak torque speed curve and a continuous torque speed curve. So the peak torque speed curve is typically limited based on the electrical constraints, things like the DC link voltage and your maximum inverter current, whereas the continuous torque speed curve is often limited on the temperature limits, so either the winding temperature insulation limits or the rotor or the magnet temperature limits. And we solve all this together to give us a maximum continuous operating curve. And we're going to show one of these at the end of today. And obviously to calculate this, including AC losses, is very important, particularly to understand what the continuous performance capability is of a design at the higher end of the speed range. Another thing that we can do with the lab module is calculate duty cycles. So this allows us to input a time, torque, and speed profile and solve this to get, with the control strategies, get losses over time, and then with the thermal module to get temperature over time. To do this, it's very coupled, because you've got to account for the amount of current you need to require to give you a particular torque, and obviously the temperature of your rotor is quite crucial in that calculation. So we fully couple and solve the duty cycles with the thermal module to give you that result. And the nice thing about that is it allows us to size the machine based on the kind of worst case duty cycle, rather than a continuous operating point, which may or not exist for the sort of real world application of your motor. Okay, so that was the sort of brief introduction to Motor-CAD, and now I'm going to start to get more into the detail of today's webinar, which is the AC winding losses. So what are AC winding losses, or where do they come from? Well, AC winding losses are caused by eddy currents, which are induced in the conductors due to the fact that the conductors are present. Well, there's a changing magnetic field that the conductors are exposed to. We categorize the AC losses into some different effects, and these effects are kind of based upon the cause of the eddy currents due to the magnetic field. So the first one we've got listed here is the skin effect, or the self-induced skin effect. And this is sort of an AC loss or an eddy current induced by the conductor carrying its own AC currents. We then have the proximity effect, and this is caused by AC currents in adjacent conductors, either strands or turns, creating that changing magnetic field and inducing eddy currents. And then the third one is a sort of an excitation from the rotor that will exist with permanent magnet machines, for example. This could actually occur at open circuit and can be significant for machines where you've got a large slot opening and the winding is exposed quite a lot to the air gap. What these eddy currents do is they create a non-uniform distribution of current in the conductor, and hence an increase in the losses and an increase in the effective resistance. And you'll quite often see or hear AC losses referred to as a ratio of AC to DC, which is a ratio of the AC resistance, or the effectively increased resistance, to the DC zero frequency resistance. So how do we deal with these different losses? Well, the self-induced skin effect can be mitigated by using smaller conductors. The proximity effect is a little bit more tricky to deal with, and one well-known technique is to transpose the winding, so twist the conductors as you move down the axial length, and that basically cancels the field, creating the eddy currents. It's the principle behind Litz wire, and it works well, but from a manufacturing and cost perspective, it can be prohibitive. The other important thing that you can do is look at the height of the bundle in the radial direction. So if you look at this picture here that I've got on the right-hand side of the screen, this shows a winding cross-section with a multi-stranded winding, and you've got the different turns highlighted in different colors and multiple strands making up that turn. And the height of that turn in the kind of up and down the slot has a huge impact on the level of AC losses due to the proximity effect. And it's actually that height to the power of 4 is what it's proportional to. So you can see that small changes to that height can make a massive difference to the amount of loss. The other aspect is where we position the turns in the slot. So you tend to get a much higher leakage field near the slot opening. And if you can move the conductors away from that slot opening where you've got the biggest leakage field, then you can reduce your AC losses, and you'll sometimes see designs where the full slot isn't utilized to pack conductors in, because it's better to push the conductors down the slots. The final thing that we talked about was the rotor excitation effect, and this can be solved by closing the slot opening or magnetic slot wedges, and we can also again look at the position of the turns within the slots. Typically with machines that we see and we design and deal with, the proximity effect is the most significant aspect, and often the most challenging to deal with, and it's the one that we sort of concentrate most on when we're doing the calculations. So this slide talks a bit about how the induced eddy currents scale with frequency, and this really depends whether the eddy currents are in the resistance limited region or the inductance limited region. So at lower speeds, or when the eddy currents are not too large, generally you see a pattern where the eddy currents scale with the square of the frequency. As the frequency becomes higher and the eddy currents become larger, these become inductance limited, and the increase with frequency kind of flattens off a bit, and that relationship to frequency squared changes. This transition tends to occur when the skin depth becomes smaller than the turn height. Okay, so that's a brief bit of theory on AC winding losses. And now we're going to talk about how we calculate these in Motor-CAD and account for them during the design process. So we've got two different methods in Motor-CAD EMag, and the first one I'm going to talk about is the eddy current solution in the finite element. So in Motor-CAD EMag, as I mentioned before, we have a 2D transient finite element solver, and this basically solves the eddy current diffusion equation in any conductive region to calculate the eddy currents and the uneven current density distribution in each of the conductor. So we simply take the conductors, mesh them in our finite element, and solve the eddy currents to find out what the total sort of overall joule loss is in each conductor. This can be quite time consuming. The meshes have to be quite detailed, and it does slow the solution down quite a lot. So to do this, one of the assumptions we make is we only mesh, or we only place the conductors in a single slot in the FEA solution, and that helps us keep the computation time to a minimum. Because it's a 2D solver, we assume that there's no AC losses in the end windings. And then the third aspect, we talked about transposition and how that can be used to mitigate the proximity effect. Well, we don't actually account for any transposition in the solution here. So we assume that the axial cross section, the radial cross section, is consistent as we move down the axial length of the machine. We've got two images here on the right, and these have been taken from the solution in Motor-CAD. So the top one shows us an instantaneous eddy current distribution in the conductors during operation. And then the bottom picture shows the loss distribution in the conductors averaged over the full electrical cycle. And what you can see here in both of these images is that as we expect, that the AC losses and the uneven current density distribution is much higher nearer the slot opening. So the AC losses distribute themselves unevenly in the slot. Whereas in the conductors nearer the back iron, you've almost got a DC excitation there, so hardly any uneven current density distribution. So this was a hairpin winding solution that was shown with quite large rectangular type conductors. The other type of winding that is quite common is sort of the multi-stranded bundles, where in this case we've got, I think, 7 turns, 6 or 7 turns or something, and each turn is made up of a number of strands. And in Motor-CAD, what we've got is we've got an editor there which allows us to automatically generate an initial distribution which assigns each individual strand to a turn, but then it allows users to vary that as well and play around with the shape of the bundle and the ratio of bundle height to bundle width. And as I mentioned before, that can make a really significant difference to how big the AC losses are, particularly if you're looking at this kind of slot opening area. So again, we do exactly the same thing once we've set this up and we solve the solution in our finite element eddy current diffusion equation, and we get the loss per conductor and then we can use that to calculate efficiencies and temperatures. So that's the finite element solution. But as I mentioned, it can be quite time consuming. So we've developed another method which is designed to give accurate results, but without requiring us to draw and mesh each conductor in the finite element solution. And we call this the hybrid model because it still uses finite element, but it's a combination of finite element and analytical methods. So the way this works is we rather than meshing the conductors in the finite element solution, we just measure the leakage flux and the flux density in the slot region during operation. And using that profile, as you can see here, of the flux density in the slot over the operation, we use that with an analytical equation to calculate the eddy currents in the conductors. And this gives us a much faster solution than the full FEA. And in a lot of cases, very similar accuracy. So this is very good for windings where we've got a single conductor per turn. So most concentrated windings or hairpin windings. With the multi-stranded bundles that we showed on the previous slide, it is a little bit trickier. And what we tend to do is we calibrate the model using the full FEA approach for one operating condition, and then we use that hybrid model from then on to calculate different operating conditions. The other assumption that this hybrid model makes is it only counts for the proximity effect. So the skin effect is neglected, but in a lot of cases, the proximity effect is much more significant than the skin effect. And we're going to show a little bit of validation of this method in the next few slides. So in the next few slides, what I'm going to do, I'm going to compare the methods on some different machine designs with different windings. So we've chosen 3 machines. We've chosen them specifically because they represent kind of the range of permanent magnet machines that we see a lot of, and they've all got distinct sort of winding approaches. So it's good to compare the AC loss model on these different varieties. So the first machine type we look at is a concentrated wound interior permanent magnet machine for a P2 plug-in hybrid or hybrid electric vehicle application. In this case, it's a machine that probably has a segmented stator, and it's got precision wound coils around the tooth and a single strand per turn. The second machine that we're going to look at is a distributed wound interior permanent magnet machine for a P4. This might be an electric vehicle traction application. This one has multi-stranded turns made up of small bundles from round conductors, as we have shown earlier. And then the third type of machine we're going to look at is a hairpin wound machine with 4 large conductors, large rectangular conductors. And these are very well known to have problems with AC loss, and it's really important to account for the AC losses when you're analysing and calculating performance for these types of machines. So I'll start with the single strand machine, and it's as I mentioned, it's an IPM machine, and it's 24 slots, 16 poles. And we took the full FEA model and calculated the AC losses in the conductors, and you can see the eddy current distribution here in the top right hand side. In this machine, because they've only got a single strand per turn and the strands are quite small, thankfully the AC losses are not too significant. But if you compare the full FEA model to the hybrid model, you get a real big difference in the sort of calculation time. So the full FEA model takes 15 minutes to solve a single operating point, whereas the hybrid model only takes about 30 seconds. And if you compare this over one operating point but range of speeds, you can see here this plot shows a very good correlation between the two models. So it shows that in this case, we can probably rely on the hybrid model and save us a lot of time in our design process. Okay, so the second machine, as I mentioned, is a multi-strand winding with multi-stranded bundles. And again, we've got this big time difference. So the full FEA model takes 12 minutes to solve, whereas the hybrid model 30 seconds. We can get very good correlation between them, but it does require us to have an initial calibration from the FEA model. And what we can do with our sort of design workflow is maybe when we do a design, we can do one full finite element solution, get a calibration factor for our hybrid model, put that in, and then we can use that hybrid model as we move further on and try to calculate lots of different operating points, or that should be fine as long as we don't make too many major design changes. This slide shows us kind of the interface for Motor-CAD and shows us where we can make this hybrid model. If I know that quite a few of our existing users are online today, and they might not recognize this interface, and obviously it's something we've been developing. So we've got this hybrid model adjustment factor in here, and this allows us to adjust the hybrid model for these multi-stranded bundle cases to match the full FEA model. The bundle aspect ratio is more of a physical parameter, and that physically represents the ratio of height to width of each of your bundles. Okay. And then the final machine design is a hairpin winding. So again, we can do a 72 slot, 12 pole machine. We've got really large AC loss in this machine, but it's not uncommon from machines that we see in industry. And I think the use of these machines really depends on the actual specific driving cycle of the machine, or the duty cycle. And that's one of the really big advantages of Motor-CAD, is it allows us to take this machine, and where you might rule something out before, you can say, well, yes, the AC losses are really large at high speed, but because we're only operating there very transiently, this is the best solution, best system solution is to use our hairpin winding. So in the previous two slides, or previous two models, basically the eddy currents causing the AC losses were only really resistance limited, and they scaled effectively the square of the frequency. In this one, because the AC losses are much larger, the eddy currents actually become inductance limited from a much earlier speed, and actually we have to make some changes to our hybrid model as well internally to account for that switch. So with the hairpin windings, a bit like the concentrated winding, we only have a single conductor per turn, and that means we don't have to calibrate the models, and we can do a like-for-like comparison between here, and we get, as you can see, pretty good correlation between the hybrid and the FEA model. It starts to diverge a little bit at maximum speed, but again, for an initial design process and iterating things, the hybrid model shows very good results. Okay, so that's the how we calculate them electromagnetically. So what we want to also understand is, well, what the effect of these AC winding losses is on the temperature of the machine, and how do we account for that kind of uneven loss distribution in the slot. So obviously that uneven loss distribution, that can give rise to some localized hotspots. If a large proportion of the loss is concentrated in one small area of the slot, then we're going to get a big temperature rise there. To model slots in Motor-CAD and our lump parameters, the thermal model, we don't create a network that represents each individual conductor, as that would create a very large resistance network, and again, it would slow down our simulation. So what we do is we use these homogenized kind of cuboidal elements that have representative thermal conductivities to represent the slot. And we can describe our slot as much or as little resolution as we like with these cuboids. And in this case, we're using a kind of a skewed distribution, where we use more cuboids nearer the slot opening where there's bigger AC losses to capture the detail, and then towards the back of the slot we have just one larger cuboid as the current density distribution is much more even, and we don't need such high resolution. So when we calculate the AC losses with the EMag module, we're calculating them either per cuboid or per conductor. And when we pass them to the thermal module, we actually pass the losses per cuboid. And this allows us to, in the thermal model, obviously calculate that temperature gradient in the slot and the uneven loss distribution, and calculate the corresponding winding hotspot. So you can see here throughout the slots on the right hand side, I've got the detail kind of lump parameter thermal network there split into the 5 cuboids. You probably can't see, and it's not big enough for the loss distribution, but I'm going to show you in the live example shortly. Okay. So how do we validate this cuboidal element approach? Well, we also have a 2D finite element thermal solver in Motor-CAD, and what we can do, we can map the AC winding losses per conductor calculated in the EMag module to the AC winding losses per conductor in the thermal module, and we can calculate a sort of a 2D section of the machine that looks at the temperature distribution in the slots. So this is not the full model. It doesn't account for the end effect. It doesn't account for our convection. It's a simple representation of the slot with some boundary conditions. But what we can do, we can take this and compare it to an equivalent lump parameter model that uses the cuboids and check that we get good correlation of the hotspot temperature between the lump parameter thermal model and the more detailed FEA. And if we find actually, we want a little bit more detail, we want to capture that hotspot a little bit more precisely, then we can do that by increasing the resolution of the cuboid. So if your question is, well, how do I know how many cuboids to use? What's the right number? This is the kind of approach you can use to decide what resolution that you need to capture the winding hotspot. Okay, so the final module we talked about was the lab module, and this is the efficiency maps and the duty cycles. And how do we account for the AC losses? Well, AC losses are variable with operating point, and they're variable with frequency. So what we do is for each cuboid we map the AC losses as a function of stator current magnitude and phase advance. And we basically build these response surfaces for each cuboid, and you can see it here on the right-hand side, and how the AC losses are changing in terms of current excitation. We also obviously scale it with frequency, and this goes back to our scaling thing before, where we had one section where it's resistance limited and then inductance limited, and we can affect the scaling depending on what level the eddy currents are at. The lab module currently only uses the hybrid model. Doing this sweep is a lot more efficient with the hybrid model, and our suggested workflow is if you wanted to validate the hybrid model with the full FEA model first, and then once you're happy with the hybrid model, you can use that in the lab module to do your efficiency maps and torque speed curves and duty cycles. The other thing is that the variation with temperature of AC losses is important to capture, and actually not just in the lab module, but in all of the modules, we account for how the AC losses actually reduce as the winding temperature increases, whereas the DC losses increase as the winding temperature increases. Okay, so I'm now going to move on to a live sort of demonstration of the calculation in Motor-CAD. So hopefully this will go smoothly. So I'll just exit out of here and minimize this one for a minute. So hopefully on your screen, you should be able to see a version of Motor-CAD open now with a permanent magnet machine. So this is an interior permanent magnet machine. It's a 48 slot, 8-pole machine design, and it's got a hairpin winding. It's designed for an electric vehicle traction application. So if I go to the winding cross section here, you can see the 6 conductors and how they're positioned in the slot. So they're rectangular conductors with I think the copper width is 4.3 the height is 3.3 millimeters. So we would be expecting some quite significant AC losses in here. We've also got the winding editor here, so I can see how the coils are laid out in the machine. And if I go to the linear pattern, we can also see another representation of the conductors in the slots. Okay, so we take this design and I move to my calculation page. What I'm going to do here, I'm going to calculate the AC losses. To calculate the AC losses, we want to first set it up in the interface, which is here in the input data settings, and I can show you the options here. And this is kind of the things that we've been talking about in this webinar. So you can see we've got the hybrid model and the full FEA model. We've got the bundle aspect ratio parameter. We've got the adjustment factor for comparing the hybrid and the full FEA model. And we've got the cuboids here where we can set the number of cuboids and the distribution of those cuboids. If I go to my winding here, you can see how these cuboids are placed on our conductors. So what I've done is I've put 4 cuboids in the slots. Basically 3 cuboids surround the first 3 conductors. So we've got kind of a cuboid per conductor. And then I've got 1 larger cuboid for these 3 conductors at the back of the slot. So I'm going to do a calculation now, and this is going to be at a particular operating point, which is 6,000 RPM, 350 amps RMS, and a phase advance of 63.7 degrees. So this is the hybrid model, so it's doing a full FEA solution, but it's not drawing the conductors or meshing the conductors. And I'm doing this live. And if I go to the EMag Netics page here, you can see it solving. And if you look to the slot at the top of the screen, you can see a lot of lines in the slot, and that's where the flux density is being measured in the slot. And it's what we're going to use in our equation shortly to calculate the AC losses. While it's solving here, I can also look at things like the torques. This is our virtual work torque that's calculated, flux linkages, and terminal voltages. Okay. So that calculation is completed. It was done in under a minute, so quite efficient. And if I wanted to look at the losses, I can just go to my output page here, output data losses. So the output data gives you a lot of information about the machine, things like the torque, the voltages, the inductances, phasor diagram, and flux densities and things. In this case, we're interested in the losses, and we can see the sort of the calculation of all the different loss components in the machine and divided into the different sections of the machine as well. So we've got our DC copper loss here, which is 2.8 kilowatts. Our AC copper loss calculated from the hybrid model. We've got a very small magnet loss here because that's been dealt with through segmentation. And then we've got some iron losses that have been calculated as well. So in total, we've got about 6 kilowatts of loss, and almost a third of those are from the AC winding losses. So that you can see it's a real significant effect, and you couldn't really accurately calculate temperature or efficiency without having this kind of approach. So if I wanted to compare that to the full FEA model, I've actually got a pre-calculated one here where I've solved exactly the same model, but with the full finite element solution. So I can jump straight to the FEA plot, and what I'm going to do first, I'm going to show you the eddy currents in the conductors as it solves. So you can see here, this is just replaying the calculation that I did before. It took a few minutes, not too long, but a little bit too long for us to show live today on the webinar. So it's calculating the current density distribution in each conductor across the rotor steps. And then if I go to this on-load loss, I will also be able to choose and zoom in here and look at the loss distribution in each of these hairpin winding conductors per conductor. If I go back to my hybrid model here, you can also see the AC losses how they've been calculated per cuboid. And you can see here, you've got C4, conductor 4, or cuboid 4, sorry, which is nearest the slot opening, whereas the cuboid 1 is nearest the back of the slot. If you remember, with the hybrid model, we calculated about 1.8 kilowatts of AC loss. And if I wanted to compare that to the full FEA model, I can look here and I can see that I get very similar 1.7 kilowatts calculated with the full FEA model. So again, in this case, we get very good correlation between the two models, and I haven't done any calibration here at all. With the full FEA model, what we do also get, which is quite nice, we actually get the AC losses per conductor. So I can see I've got my turn 1 with my largest loss here, with almost a kilowatt actually of loss just in that first conductor. And you can see how significant that AC effect is and the uneven loss distribution. Okay. So I'm going to go back to the hybrid model now, and I'm going to show the coupling to the thermal module. So I've got the calculation page here, and you can see this is where you've got the losses to thermal coupling turned on. We could actually do an iterative solution as well, so bring the temperatures back and resolve the EMag module. Today I've just done the one pass coupling, so I've just taken those losses and I've passed them to the thermal module. Okay, so I'm going to go to the thermal module now. Once I go to the thermal module, you see the housings drawn on the machine, and this shows all the cooling in the machine. This particular machine is an oil-cooled machine. It's got axial kind of channels going along, which then drip oil over the stator winding. And it also has oil that's passed along the shaft and thrown off onto the inner surface of the end winding. So it's a sort of fully oil spray cooled machine. So if I go to my losses now that have been input into my thermal module, you can see they've all been automatically passed across, including the AC loss component, and we will have also have passed them across per cuboid. So we'll be accounting for that uneven loss distribution. I'm going to solve the thermal module now, or solve this thermal model. I'm going to solve it at the same operating point, and I'm going to solve a steady state solution here. So I'm going to start here. You can see this is the representation of the lump parameter thermal network, and we can easily see here that we've got the nodes calculated. The colors in this diagram all kind of represent the same colors that you get in the geometry drawing. So the yellow part is the winding, and I can see that I've got 172 degrees C in the active section of my winding. If I go to the detail tab here, I can also see, if I zoom into these cuboids, I can see how the losses have been distributed per cuboid. This cuboid here is representing 3 conductors, so it has a large loss, and then you can see the increasing loss distribution as we go towards the slot opening. And actually that smaller conductor, that conductor at the bottom of the slot near the slot opening has got almost the same amount of loss as the 3 conductors near the back of the slot. Okay, and I can also look on my radial cross sections and see my peak winding temperatures here as well. So the final module that I was going to show here was the lab module. So the lab module, as I mentioned earlier, works by kind of mapping the machine using the EMag solution, a range of different currents, phase advances, and some different frequencies. And it's building models of the saturation and the flux linkages, but also the iron losses, the magnet loss, and obviously the AC winding losses per cuboid. So we've mapped all of these, and we put a lot of effort into making sure this is solved fast. So it uses a kind of multi-threaded approach and solves lots of different operating points in parallel. So again, this model build should only take minutes to solve and allow you to work iteratively. And then once we've done that, we can very quickly generate efficiency maps. So I'm going to show an efficiency map here of my machine. on screen. So this is an efficiency map of my machine that I was showing the design of, accounting for all the different loss components. And if I wanted to look down here, I can scroll down and I can see total losses. So this is a loss map against speed and torque. And I've got stator copper loss, and this is broken down into the DC and the AC components. You can see quite different profiles of the DC loss basically being proportional to the currents, and the AC loss being proportional to the current and the frequency. Another thing that we can do with the lab module, I mean, there's lots of functionality here, so I don't have time to show everything today, but I wanted to show the thermal envelope calculation as well. So this is where we basically set a maximum temperature for a winding, or we could set a maximum temperature for a winding and for a magnet and solve across the full operating range. In this case, we've gone from 1,000 RPM to 12,000 RPM. And the software will tell us what the maximum torque that we can produce is continuously. So I can show this on the screen here, and you can see in this case we've got a maximum torque of 350 Newton meters at lower speeds, and this kind of falls off as the speed increases. And you can also look at the power here, and we can see we reach peak power of about 150 kilowatts before this again starts to fall off with high speed, and I would think that part of that behavior is definitely due to the larger AC winding losses. We can also see this here if we look at the stator copper losses. So they remain reasonably level actually throughout this speed range, but the distribution of DC to AC changes. So as we go through the speed range, the current is reduced, and the AC losses are increasing quite significantly over the speed range, whereas the DC component is falling. Okay. So I think that sort of covers the sort of brief example and how we account for all the AC losses in all the different modules. Hopefully some of you guys have managed to ask some questions. So what I'm going to do now is going to hand over to Murcha, and in the last few minutes he's going to pick out some of the questions that have been asked throughout the webinars and give you some answers to them.
Okay, thank you very much, James. Hi, everyone. So I'm going to try to answer to a few of your questions. We have recorded all your questions actually, and those that I cannot be answered live right now will be answered through email or private communication. So let's see. I'll start. Obviously, the first question that was asked by several of the attendees was, how accurate is the AC losses model implemented in Motor-CAD, hybrid and FEA? Was this validated versus experimental data? So we did validate these both models, first of all, versus 3D finite element completely models. So we had examples for both hairpin winding and stranded wire topologies that we modeled it in 3D finite element and then compare it with our results in Motor-CAD, and results were pretty good. Also, we are taking some measurements through different projects. We've been provided access to measurements for one of the designs that we have helped with different customers, and again the agreement was pretty good, so within the acceptable divergence limits. Another question was related to the fact that we calibrate the hybrid method using the full FEA method. And for example, in the case either a hairpin winding or stranded wire, the distribution of the losses within the slot can be captured accurately with the FEA. And the question was, how can we calibrate the same thing using hybrid because through calibration we'll have just the total loss calibrated. In Motor-CAD, we do have a method to distribute the losses per cuboids or per conductor. So with some extra work, it is possible to associate the correct amount of losses for each conductor or for each bundle. Other question was how AC losses will vary with temperature. Unlike the DC losses, the AC losses are proportional to the conductivity, electrical conductivity, or if you want, they are inverse proportional to electrical resistivity. So while the DC losses, copper losses will increase with temperature, the AC losses will actually decrease if your conductor get hot. So for the same frequency and load, if the winding gets hotter, we can expect that the AC losses will go down while the DC will increase, such that at some point it's possible to see actually a constant overall amount of losses, even though the temperature has increased from one moment to another. So I'll try to pick a couple of more questions because to the time limit, we can probably extend all the way to 6 or 7 more minutes. So was question, what can we do about modeling twisted wires or transposed wires in the slot? For the twisted wire, unfortunately, or fortunately, depends how you want to take it, the only reasonable method would be to do a full 3D finite element calculation, or based on some measurements to be able to calibrate the models in Motor-CAD. While for the transposed wires in the slot, we do have in plan, and we have few ideas to work on, and we will try to implement it in the upcoming versions. Possibly in 2019 we'll have something as a beta version, but obviously the calculation effort will increase significantly because to model transposed wires in the slot, we'll need to model more slots filled up with conductors to capture the effect of transposition within the slot. Let's see what other questions we got. The question was, how can we account for the end winding losses? One of the attendees is asking. So the end winding losses are considered as a DC component. As James mentioned, in our assumption that AC losses in the end winding can be neglected, it's based on the fact that typically the variation of the magnetic field for the end winding is not that significant, and therefore the AC loss component, most of the cases can be safely neglected. Well, to be honest, the only way to, if you want to validate this, will be again a 3D finite element. But from previous published papers and considering state of the art of different other publications, we consider that it's a safe assumption to neglect the AC losses in the end winding. Other question is, would the current waveform time harmonics have a significant on the AC losses? Well, yeah, it depends on the harmonics content, on the THD content of the currents. Motor-CAD software can model this. We can inject any current waveform that it's based on either measurements or some theoretical approach. The only drawback will be that will require more rotational steps to capture all the variation of the time harmonics in the current waveform, and it's difficult to make an estimation on how large will be the AC losses due to the current time harmonics. It really depends from one case to another, and obviously on the frequency of this and the amplitude of this time harmonics, how much they will influence the total losses. I think one other question was related to the material of the winding. So we have a question meaning, can we model as well aluminum winding in Motor-CAD, and from high frequency AC losses, which one would be more a better solution, aluminum winding or copper winding? This relates to previous question when I was mentioning the temperature, meaning that AC losses I mentioned, it's proportional to the conductivity, electrical conductivity, where the DC losses are proportional to the electrical resistivity. So this means that at a certain threshold frequency, two identical coils, built one with aluminum, one with copper, will have exactly the same amount of losses, meaning that DC plus AC from the aluminum will match the DC for the copper. And going above that frequency, the aluminum will start to behave better than the copper. It just depends on the dimensions on the frequency. And I think this pretty much concludes. This is the time that we had to answer your questions. I mentioned that we'll do our best to answer to all your questions that you have provided as soon as possible. And also feel free to contact us also directly after this webinar and for more information that you are requiring from our side.
Okay.
Back to you, James.
Yeah, thank you very much, Mircea, for those questions, and thank you very much for everybody who attended. I think we had really good turnout, and we actually have loads of questions, so we'll do our absolute best to try and get back to you on all of those, and we'll endeavour to keep developing and taking account of all your feedback and ideas. A few final points. Lots of questions about, can we have the slides? Will this be recorded? This is our intention. We are trying to record this at the moment, and we will be uploading it to the website, and we'll be following up with an email with a link. So hopefully that will all go smoothly. This is our first ever webinar, so yeah, but I think it should be fine. If you want to keep a bridge of all these things and more information about upcoming webinars, training, technical papers, we have our MDL Talk newsletter and our website. And then also we've got a training course coming up in October if anybody is interested. And this will cover sort of a mixture of theory and practical work, designing and analyzing different electric machines. Okay, so thank you very much, everybody, again, and hopefully we'll be doing more of these in the future. So goodbye for now.